Okay, so the next speaker is Leonid Ryvkin from the University of Göttingen, and he's going to talk about the L-infinity algebra of a symplectic manifold.
Okay, so thanks a lot. First of all, of course, to the organizers for making this wonderful event possible. And also thanks to Lucas, because he basically made 20 minutes of my talk obsolete by giving the motivation. So I'll basically be finished on time. I'll still give a slightly different motivation, which is we start with the symplectic manifold. Oh, by the way, it's written, but I'll still say this is based on joint work with Bas and Cornelia, who are here and also speak here. And it actually starts with some work of them, which is that if we have the Lie algebra of Hamiltonian vector fields, they have proven that its universal central extension is given by omega 1 divided by delta omega 2. And let's say things are compact. In the non-compact case, there might be some small c's at different places. And so maybe I should explain some of the letters. For example, the delta is a map from some Deram group to one lower. It's not the Deram differential, and it's given by, for example, the delta of alpha is contraction of the Poisson vector associated to the symplectic structure, and then to the differential of alpha minus d of u of pi alpha. And in case you're not familiar with it, if omega would be sum of dxi, dyi, then pi would be the sum of partial xi wedge partial yi. It's a bi. And I wrote it in coordinates, but it is intrinsic. So, and maybe I should also say what this map is. This map goes with using delta to the smooth functions, and then using the usual association of we map an alpha to x alpha by the equation d alpha is iota x alpha omega to a vector field. This whole talk is up to science. So if your tastes want the minus sign somewhere, just add it in your notes. And so Bas and Cornelia have proven that this is a universal central extension in a certain category of Lie algebras. And the interesting bit from the last talk also appears here. We have a Deram group divided by the image of a differential. And this is a little bit the starting point of what we have worked on. We try to find out what lies behind this. And more precisely, if we were wondering what L-infinity algebra lies behind this, because whenever we see a Lie algebra on something which is a quotient, we wonder whether it comes from a Lie-infinity algebra on the original thing. I haven't told you yet what the Lie algebra structure is. The elements here are equivalence classes of forms, and their bracket is defined by, for example, delta alpha d delta beta and the equivalence class of that. One can check that this is well-defined, skew-symmetric on the level of equivalence classes and really a Lie algebra structure. So, and we are trying to find the appropriate structure of omega 1m, or maybe a complex that includes omega 1m. So I will just give the shadow of an introduction to L-infinity algebras. So an L-infinity algebra can be seen as a Lie algebra up to homotopy. Or a Q manifold over a point, like that sort of things. An L-infinity algebroid over a point, which a little bit defeats the point of an explanation, or as a co-differential on some, I'm getting smaller, co-differential on some co-algebra. I'm being sketchy on the right because I'm going to focus on this perspective because it somehow fits the problem quite nicely. So when we have a Lie algebra, we can see it as some space, G, and a binary operation in it, on it. And the operation satisfies some equation, which is ABC minus all the usual permutations is equal to 0. And so what we are now going to do is we're going to do homotopy stuff, which means we're substituting zeros by d of something. So let's start with one homotopy level, and then it's called V2. We have the Lie algebra from before, the same equation, but instead of 0, we write d of something. I'll call this something j because it's a Jacobiator. But for this to make sense, we will need some d that maps into G0. This will get an index -1 due to logistical reasons, again, up to signs and orientations of complexes. And we have this additional map J, which for everything to work out should go from lambda 3 G0 to G-1. And this J satisfies some equality. So if one first brackets and then does J, it should be, and does some permutations of it, it should be the same thing as using J as an argument. And here one already sees that one needs also some kind of bracket between G0 and G-1. So one also needs to extend this to something that goes from G0 and G-1. Oh, sorry, yeah. Okay, so, and then the idea is one can continue the whole thing. So this is this we can rewrite into something equaling 0. And in the next step, we would substitute this 0 by a new d something and add the something to the definition. So we get Lie3 and so on. And when we take everything together, that's what we call an L-infinity algebra. So I'll just finish by a formal definition of what I just said roughly. L-infinity algebra is a Z lesser or equal to 0 graded vector space, G with some indices, and maps Li from the I-fold alternating product of G to G of degrees 2 minus I, satisfying a certain condition. And the condition is basically we use one bracket, and then we use the result of it as the first entry into a second bracket. And then we go over all possible ways to do that. And we go over all possible permutations that make sense. I will not be precise on the permutation, it's unshuffles, and we decorate with the correct signs, and this all has to be 0. So this can be relatively complicated in general, but the L-infinity algebra we are going to need is of a really simple and special kind. It's something that one can call, for example, grounded L-infinity algebra. I understand that I should not cross this line. Okay, sorry. And this has, one can do many different descriptions, but one of them is a central extension of a Lie algebra by a differential graded vector space. So I think that these L-infinity algebras have been observed and called very different names in different contexts. Rogers used them in multi-symplectic geometry. Stashev, Barnish, Fulp, and Lada used them for field theory, and there are also papers by Lazarev on it. And so this is actually the type which will suffice for our setting, which kind of makes sense because what we are doing is we have a Lie algebra and we are trying to extend it by the Durand homology chain complex. I'll add maybe a remark. So L2, L3, and so on, only non-trivial on G0, on the ground degree, that's why they're called grounded, and actually even more, they are 0 on the image of the differential, so 0 on L1, the first bracket is the differential of G minus 1. Maybe because I used different letters before L1 is what was the differential, L2 was what got the classical bracket symbol, and L3 was J, and I didn't write down the further ones. Do I understand the homotopy of the schedule correctly, that I have around 10 minutes? Okay. So normally I would now try to use a pedagogical approach where I start with the binary bracket that seems like it makes sense, and then I notice that it doesn't work, so I'm putting in a correction. Then I think, oh, I can build the third bracket, it doesn't work, I put in a correction, and so on. So that's the way I would think about it. But because this is a short talk, I'll just write down the answer, and then if there is time, kind of explain the first few steps by hand. So, to formulate the L-infinity algebra we are looking for, we need a few operators that we have already seen but not given names yet. So one of them will be wedging a differential form with omega. The other is contracting with the plus or bivector. Those are operators that go from the Ram complex to itself. One has degree +2, one has degree -2. And then we already saw delta, which I will now write in operator notation. It's the commutator between lambda and t. This can be seen as a definition. And now, with some calculating, one can see that D is also L commuting with delta, which is absolutely irrelevant for the rest of the talk, but really nice. So we define the L-infinity algebra that we wanted to find, and G0 is omega 1, G minus 1 will be omega 2. So we can have our delta from there to there. So L1 or D will be a delta. And so on until omega 2m. So we have a 2m dimensional symplectic manifold. And this will be G minus 1 minus m. And now we define the higher brackets, which is, this is the really problematic bit where you try the things that make sense and they don't really work. And the thing one would try is, so let's say it's LK of alpha 1 to alpha k. And those are all one forms because we talked about having a grounded L-infinity algebra. They are all only defined on this degree. So those are all in omega 1. So what we can do is we can just take delta of alpha 1, t delta alpha 2, and so on until t delta alpha k. And this is of course not skew-symmetric, so we add a sign and permute over the different i's and just omit the ith one in this list. So we skew-symmetrizing, maybe with a normalization. And this still doesn't work. One just doesn't get the equalities one needs for an L-infinity algebra. And to correct that, one needs an operator, which is a sum of certain coefficients. Li, the operator there, lambda I. And the coefficients are exactly what you thought they were, -1 to the k minus I minus 1 factorial, n minus 1 factorial, I factorial. Now the theory is this is a grounded L-infinity algebra, and the math from G to omega 1 divided by delta omega 2 is infinity. So yes, that's a theorem, and so, this is for a power series, but because the Durand complex is bounded in degrees, there are only finitely many terms here, and that's among all L-infinity algebras of like the coefficients are unique once this shape is predefined. Now I would just write down the first few terms because this formula is a little bit in capsule. L2 of alpha beta is 1/2 delta alpha d delta beta minus delta beta d delta alpha. L3 alpha 1, alpha 2, alpha 3 is 1/3 delta alpha 1 d blah 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 blah. But it doesn't completely work. One needs this part, but one also needs 1/2 of the L lambda of this for it to work. And L4 will have the coefficient identity plus 1/3 L lambda here. And here we thought we got it figured out. And then we calculated L5 by hand, and it turns out that a new term appears. And so on. Okay, so this is the L-infinity algebra that I wanted to show you today. More or less as a concluding remark, I should note that a simpler version of this L-infinity algebra has already been known for this universal central extension of the volume-preserving diffeomorphism groups. So if one has the exact diffeomorphism of some manifold that has a volume, then the universal central extension is omega m minus 2 d divided by d omega m minus 3. I think this is Claude Roger was shown this, at least in the compact case. And this Lie algebra actually is the quotient of an L-infinity algebra coming from the multi-symplectic manifold M omega. So basically one has the complex omega 0 going up to omega m minus 2. And one has a very similar L-infinity structure on it, just with significantly easier brackets, which are just contracting into the volume. So this is Claude Roger, and this is Chris Rogers. Okay, and at this point, I think I will stop, and thank you for your attention.
Are there any questions?
There is a question online.
Okay, you can go ahead.
I think you can go ahead with the online question.
Yeah, sorry, may I ask a question? So do you think it's possible to generalize the construction to more general Poisson manifolds?
This is work in progress. So we have an abstraction to the existence of an L-infinity algebra for a certain Poisson manifold, but we're now working on finding out which Poisson manifolds work and which don't. But there are certainly cases where this doesn't work.
And does this has to deal with the modular class of the Poisson manifold?
Which class, sorry?
The modular class.
Maybe. The honest answer is I don't know. I think the structure we found is not equal to the modular class, but it might be related.
Okay, there was a question in the audience. Some questions?
Yeah, I have a question to the talk before, to Miaskowski. What is the universal central extension for this gauge-Lie algebra where you computed the second cohomology?
Oh wait, is this question directed at me then?
Yes.
Okay, I wasn't quite prepared. I'm sorry. So sorry. Can you repeat it?
So you computed the second cohomology of the gauge-Lie algebra in general. And of course, there is a universal central extension associated to this. Have you identified it? Which is just a Claude Rocher theorem that is still on the blackboard. It is erased just now.
Oh. Yeah, actually, this is so I think Bas might talk about this in his talk, potentially. I'm not sure if he's nodding or maybe not, but the central extension has been identified in this case. But yeah, I can't cite it off the top of my head. This like I said, this might come up in Bas's talk.
Okay, Marco wants to ask the question.
Thank you. So I'll be brief. My question is connected to the first question. So does the Poisson geometry point of view clarify any of this? For example, the binary bracket, which you wrote down in terms of this delta and D. So does it have anything to do with the bracket on one forms on any Poisson manifold?
It can. I think it can be completely rewritten in. It can be rewritten in terms of delta of the one form. So it really depends only on the function. So you need the Poisson bracket and the exterior derivative to write it to formulate it. But yeah. So. And I would like to answer one question that wasn't asked very briefly. So one of Bas' students, Kevin van Helden, has generalized it to symplectic foliations, which are further Poisson manifolds that have such L-infinity algebras.
So maybe a silly question, but when you started, you show us the idea was to start from the level 2 of these homology. Then we did delta map. Is the Hodge-Cobollis map, or is something?
Sorry again.
Is this delta map the same as this Cobollism map from Hodge homology, or is something completely different?
So you mean the co-boundary?
Yeah.
The delta is the wait. So Hodge, you mean symplectic Hodge?
Yes.
So it's certainly like the normal Lichnerovich differential of the Lie algebroid associated to the symplectic manifold, but I think that the Hodge is something more complicated.
Okay, so you go from there to the functions by delta?
Yes.
Delta 2, omega 2, right?
So this is the underlying complex with.
Yeah, and then you have the natural identification with the Hamiltonian vector fields.
Yes.
And my question is, you identified some kind of natural section for this quotient? From the last one to the quotient of the omegas.
I think they should not exist in general when the like it's a two cohomology class that should obstruct the central extension from being a direct sum. So if the two cohomology is if you have a section here, you certainly have a section here. So there is a condition for that, and then I think there is even more condition to actually get to omega 1 divided by d omega delta omega 2. So there are cohomological abstractions that I cannot write down from my head, but I think it's all worked out by Bas and Cornelia.
Okay, I will ask for reference then. Thank you.
It's so good to have collaborators in the room.
Can you again interpret this for me, the infinity algebra? I mean, what does it mean? Should I think of this?
So, yes and no. To some extent, the existence of this L-infinity algebra is just, if you see the quotient, highly probable. And to actually find it, one finds a two-cos cycle in a Lie algebra cohomology with valued in a differential graded vector space. And of course, there is some arbitrarity there. But so what's striking about this one is that it is extremely natural and functorial. So the L and the lambda operators are basically fixed once you have the symplectic structure. So you don't need to take any choices. And yeah, so this is why we think this is somehow the right one or one of the right ones. Of course, one can add exact things and so on. L-infinity algebras are never unique on the nose. I guess that my hope would be that using the L-infinity algebra, one can prove those central extension results easier because one somehow desingularizes this complex that one works with. But this, so far, this is a hope in progress.
Okay, I'm not sure if we have time for any more questions. So let's take the speaker again.